Good morning. Welcome to the tutorial. So I am Arup Chakraborty. I work in Ventana Micro Systems in the performance team, and my friend Knute Lingaard, he works in SiFive performance team, and we have been driving the RISC-V performance modeling SIG, as a part of which we have been developing this performance model, and we are going to go show a demo, a tutorial on how to use this model today. Okay, so here is the a visual flow of how the tutorial will go. So first we will talk about how you can use a binary you can run it on a functional model that has been instrumented with a library called STF library that generates a trace, an instruction trace, which captures the order of retired instructions. Then we would mention some of the utilities that are there in order to look at this trace, analyze this trace, and so on. And then Knute will take over and he will show you with an example trace how to run it on Olympia, which is the name of the model, how to generate reports, various pipe outs, which is pipeline visualization diagrams, generate stats, and so on. And finally, we would also show you how to use this pipeline visualization tool called Argos, how to do time series analysis, and finally we'll put together the entire thing, doing a sort of a bottleneck analysis for dry stone.
Okay. Yeah. So we can go right into it. Oops, little preview there. Okay, going to the wiki.
Yeah. So now we are going to the wiki. So I will give you a quick overview of what the model is, this RISC-V performance model. We already talked about it yesterday in the talk, but in case you have missed it, here is a very quick overview. So this model is a C++ based model written using a framework called Sparta Modeling Framework, which we also introduced yesterday. And it's an example model of an example typical superscalar out-of-order processor. The pipeline in the model, can you show the example?
No.
There? Yeah. There.
Go ahead.
Yeah. Cool. So the pipeline over there is very simple, rudimentary, what you expect out of a superscalar processor: in order fetch, in order decode, rename, dispatch, out-of-order execute, in order retire. And going back to the tutorial, and then so we already talked about the tutorial flow. Now I'll talk about how to generate the trace. So in order to generate the trace, what we need to do is we need to instrument a functional model with this STF library. The STF stands for Sparta Trace Format. It's a library. It has its own API, and using which you can generate a trace. The trace itself, we are not going to show here how to generate the trace, but there are instructions over here. How can you apply a patch to the functional model Dramajo and run Drystone through it and generate the trace. The trace itself is a binary file. It's a sequence of retired instructions, and there are some tools out there in the STF repository to look into the trace. So for example, in this case, we are showing that there is this tool called STF dump, which can show you the content of the trace. So in the first instruction, as you can see, there is it shows the size of the instruction, it shows the address of the instruction, the opcode, the assembly, and also some metadata that what's the virtual address of that this load is pulling data from. And so then in order to, so how do you run this trace? So the running this trace is on Olympia is just to invoke Olympia with the trace. That's it. Now Olympia also supports a simpler form of a trace, which is just a JSON file, a text file, and the format is pretty self-explanatory. That so you have to specify the mnemonic, you have to specify the source register, destination register, immediate virtual address, And so if you can see that here we are loading a value from a specified address to X5, and then we have an add operation that uses that register. So there is a load to add dependency here. And so using this trace, for example, you can see what's the load to use latency of your architecture, okay? And yeah, so now I'm going to hand over to Knute, who would actually would run these commands on the computer and actually go through the demo.
Thank you, Arup.
Yeah.
So what we decided to do is, instead of having essentially a PowerPoint presentation on the tutorial, we actually decided to make it more interactive. So on the left here, I have my Mac actually here running Olympia. It built it, and it is available for us to use. You can build and run on Mac OS and Ubuntu, I think CentOS and so forth, or different types of platforms. So thank you, Arup, for going over essentially the basics of it and going a little bit reminder of what we did is essentially there are directions here that we did provide, as Arup said, to be able to generate your own trace. We do have, it comes with the repository for Olympia, a version of Drystone that was traced, but only during the actual main loop of Drystone itself, the actual iterative block. And so for the idea is that the trace itself does not contain the preamble and postamble part of Drystone. You only care about the actual iterations, the actual things that you can calculate DMIPs off of. So following the directions you can on that, it's also part of the tutorial. The tutorial is in the RISC-V performance modeling repository. All the directions are there. If anything looks wrong or is difficult or problematic, please file an issue with us and we'll get right to it to fix it. So let me show you an example of how you can run that Drystone trace. It's as simple as Arup was saying, is just simply providing essentially Olympia with the trace itself. So copying this command line and running it over here, it will run the simulator, and you can see the simulator invokes, and what it does is it creates that pipeline that was originally shown by Arup in part of the core example. We have a fetch, a decode, execution blocks out of order, and so forth. When it's finished running and executing, it'll provide, because I provided a command line flag called auto summary on, this tells me what I'm asking this simulator to do is, in the background, go ahead when simulation is completed, go through and collect all the counters and statistics and so forth, and just dump them as raw counters directly to the command line. That's useful and not at the same time. At least you get a general idea that the simulator ran and it actually did some work. For example, we do have in this example here, I have Olympia configured. So it has one ALU block, one FPU block, one branch unit. And you can see the distribution of instructions for those, plus an load store unit. And then basic statistics and counters that we've instrumented so far in the model. Again, this model is only a few months old. It allows you to do LSU, how many instructions are dispatched, retired, TLB hits, and DL1 cache hits misses, which we do model that inside Olympia. So this is the general use, a simple flow where you just simply provide Olympia with the actual trace and tell it, I want to generate a general summary. And that's the first step you can do if you just want to start playing with it. But that's not necessarily interesting. What you really want to do is you want to be able to tweak parameters. I mean, the whole purpose of performance analysis and architecture development is you want to try trade-offs. What happens if we add an extra unit? What if we increase the size of a buffer or a queue? What if we change the behavior of the way a pipeline operates and so forth? All those can be put behind parameters using the Sparta modeling framework, which supports parameters. Use those parameters, you can change topologies, you can change behaviors, and of course, there are all those other things at runtime. The whole purpose and point of this is not to do compile time types of changes. So Olympia has this concept of essentially allowing you to say, what is the, using the Sparta framework and its internal components, you can actually query things such as, show me the parameters. What parameters do you support? And so the no run flag, by the way, is a nice little convenient way to tell the framework what you're interested in doing is something, you're looking at inspecting the simulator. Don't run anything and don't expect a workload, and for goodness sakes, don't crash because there isn't one there. So a no run is very handy that way. So you can say Olympia no run, and then you could do things such as like show parameters. And if you show parameters, what it's going to do is it's going to provide a really gobbledygook looking thing, but here, there we go. It's going to show you the actual tree of what is being built internally to the Sparta model. So Sparta, as I mentioned earlier, if you happened to catch our talk yesterday, the Olympia uses the Sparta's tree node hierarchy and concepts to actually build a simulation environment. So you might be familiar with some of these things. If you're a hardware engineer, you might be familiar with some of the nomenclature that we use. For example, there is a concept of top. Top is your root node in the entire CPU design. And then you can have components underneath it, like a CPU, and a CPU consists of cores if you want to do if that's how you're doing your layout, and that's your nomenclature. Olympia does support multiple cores, and so you can have core 0, core 1, core 2, core 3, and the idea is it instantiates all those components. In order to do that, one extreme hardcore rule is you don't have non-constant statics that are actually built inside the simulator, because that's just bad. You don't want to have any conflicts. But in general, when you look at this, underneath the core we have a fetch block, and in the fetch block we have a decode block, and here are all the parameters that you're allowed to tweak for each one of those. It's really easy to add a parameter. You just another line in a file to the fetch block itself, add a new parameter, you give it its type, what kind of type of parameter it is. The types of parameters you support are all the basic POD types, such as integers and characters and so forth, but you can also do vector, an STD vector of parameters, STD vector of types, POD types, a vector of parameters. You can do kinds of matrices, you can do all kinds of things. That enables you to define topologies, it defines latency charts or matrices and so forth. So this is one way to examine all the types of parameters that are there. If you want to be able to actually write them, for example, to a file, which is very handy, you can actually say something like write final config. And the idea is that let's call it config1, the YAML. And it outputs, and I misspelled that, but who cares? The idea is it outputs a config1 YAML, and now we can look at it and say it's actually a descriptive file. So now you can actually edit this file and make changes directly to these parameters, and then you can load that back into Olympia, saying this is what I want you to use instead. That's one handy way to do it. But if you can see, what we have here is just the parameters and their actual types and whether they're defaults or not. But it's not very helpful, especially if you want to know what does that parameter mean. So you can say write final config verbose, and since now I have actual descriptions. So for example, num to fetch, number of instructions to fetch. You know, it actually instruments it because we chose YAML because you can use comments. That's very handy. And you can but it outputs the actual verbosity of the parameters themselves. So that's one way you can do it, is you can see examine parameters and what's there and what's handy. The other option, though, is how do you change those parameters? Well, as I just said, you can dump a final configuration, change the YAML, and then there's a read final config where you can read that configuration back in. But if you just want to change one specific type of parameter, you can literally just say -p, and you can specify the actual path to that parameter and change it explicitly. So I can run a dry stone trace again where I increase the dispatch queue depth to 12. Its original value was probably something around 6 or so forth, and it will slightly change the IPC of this trace, because now we have more depth that we can do and more instructions can be fetched into the machine. So that's an example of how to do it essentially on the command line. And of course, this here is another example. I won't go ahead and do this, but you can actually create a smaller YAML, not a final config YAML, a very tiny one. And then you can specify the path of specific parameters that you want to change, put those in a YAML file, and using a -c option saying instead of a -p, which is one parameter, -c is a config file with multiple parameters. You can read that in, and then you can change multiple things at a time. The whole concept and the reason all this is put together is one simple thing. You have a performance model that represents your microarchitecture. And what you're going to do is you have a bunch of workloads that you run through your actual simulator. And what you want to do is you want to do an experiment. So you say, okay, I need to draw a baseline. So I have a baseline of how the configuration is. You run it off and say you farm it off to an LSF farm or something like that. And you run all those workloads and you get your reports. At the same time, you can use a YAML file, -p options, or a final config, change it, and then run everything over there. Same simulator, same code base, everything's the same, nothing's read and recompiled, and then you run it. And now you've got two studies, essentially one study that has two configurations to which now you can do your comparison to see where are my uplifts and where are my bottlenecks. So these are all the parts that allow you to actually instrument it. Now, those are parameters, basic single tweaking of individual pieces. We also added this concept of architectures. So let's say that you have different architectures inside house. So you have a simple core, a little tiny core, or you have a medium core, a big core. So what you can define are architectures that allows you to say, okay, this is a small core representation, and here are all the parameters that are associated with it. Then you can say, I have a medium core. And with a medium core, what you can do is you can include or in this example here, I have a big core. I create a big core. What you can do is you can include the medium core. Well, a big core is a medium core with some more tweaks here and there. So you can build on top of YAML files. The whole purpose and point of doing these types of things with architectures and so forth is you don't define, what I'm trying to say, you don't want to say, look, I am creating essentially this concept of when you have a different type of behavior in specific one of your blocks, this is what I'm trying to get to. When you have a behavior that you're defining in your block, you don't want to say, this is my behavior of a big core, this is the behavior I want of a small core. What you do is you define behaviors in your simulator specific to parameters. What I mean by that is that, all right, I have a specific behavior that I've defined. My medium core and big core can do that behavior, but my small core can't. So I have a medium core, I inherit from small core, I say the medium core does this behavior. Now I create big core. Big core inherits from medium core. Big core also does that behavior, which is perfectly fine. So it builds on top of itself as far as a hierarchy. In the simulator, you should never, ever have an if statement, so to speak, that says, if we're a big core, do this. You shouldn't do that. You should always have something, if we have this behavior, do this. And you define the behaviors in your architecture. So, okay. So now that we have the concept of architectures and you can run these architectures, and included with Olympia are 3 different architectures, small, medium, and big, and we'll show an example of how to do that. We now move on to what can you do with that stuff. Okay, now I got a simulator, I've instrumented, I got counters, I got statistics, I've got all kinds of definitions, I've got my architectures. I want to do a study, I want to do an analysis. How do I do that? And so the idea is that, all right, you need data coming out of the simulator. And the way to do that, one example I showed at the very beginning of this is with the auto summary, which dumps everything to the screen, which is mostly useless. But it gets you a good idea where you are. What you really want is you want detailed reports. But more specifically, you want reports you can control. So what that means is that if you're running Drystone, for example, and you do one iteration, well, what happens in Drystone in one iteration? You've got cold branch predictors, you got cold iCache, you got cold dcache. One iteration doesn't tell you anything about your microarchitecture, especially since Drystone does lots and lots of iterations before it spits out a DMIPS result, right? So what you want is you want to be able to run through Drystone multiple times, but you only care about after a specific period of time has elapsed. Maybe, for example, so many iterations have gone by, or so many instructions have gone by. So the way you can do that is you can use the Sparta's reporting mechanism to actually fine-tune reports that you want spit out. Reports come in 2 forms. One report is called a definition file, and this is a link to the Sparta documentation for that, and a contents file. The best way to think about the difference between these two is a definition file says how you want data to be collected. A content file says what I want to be collected. Definitions include content. Content know nothing about definitions. I'll give you an example. I want to define in a definition file, I want to collect Drystone after 100,000 instructions have gone by. That's how I want the report to be collected. What do I want collected? I want all the core stats. I want just dispatch stats. I just want Rob stats. You can say what you want collected, and then you can say what format you want those files in. You can say I want it in a CSV, HTML. I want it in JSON, I want it in YAML, I want it in text. All kinds of forms you can do that. So I already gave an example of the auto summary, so I won't go over that one again. But here is a simple content file. A simple content file has some very simple keywords that Sparta understands, and all this is documented in Sparta's framework. A core stats file, which is defined in the reports directory over here. As soon as I get my fingers untwisted, we have a core stats.yaml file. Inside it is a content, and it tells you this is what you want collected, not how, what you want collected. And you want to say, I want to create a report, auto-populate it with every single statistic that I have defined in the simulator where the attribute is not hidden. You can actually define statistics that you want to hide. So for example, you really don't care. It's very interesting, but not necessarily not what you want. Utilization stats of a buffer or a queue. If you have massive buffers and queues, you'll get hundreds, if not thousands, of these utilization stats, which are very helpful if you're looking at trying to figure out maybe watermarks and so forth. But overall, that's not what you're interested in, and it's sucking up a lot of disk space, especially when you do a study. So you can actually say, I want all of those things hidden. And you can, when you create the statistic or the counter in your simulator, you provide it the attribute hidden. And it'll say, okay, this is a hidden statistic. I don't want it. So the way to run a report is a little bit tricky. But I will disassemble essentially the command. So over here, I pasted Olympia. What I want to do is I want to generate a report. The report position where I want it to start reporting the content from, what I want to start collecting from. I want to start collecting at the top node, everything from the top node down. This is the content file that we were just talking about. The number 1 means send it to standard out. Number 2 means standard to standard error. Anything else means a file. And then finally, how do I want that? How do I want it collected? In a text file. And so we'll run 1 million instructions of Drystone Olympia. And it generated a much simpler report. If you remember, the auto summary one was huge. This one is now much smaller, much more tight, a little bit more specific to what you're potentially looking for. And it dumped everything to standard out. If you want to put it to a file, replace 1 with essentially your file that you're interested in. Here's some neat things you can try with this command. For example, maybe I'm not interested in just in top. Maybe I just want to see top.cpu, a core 0, dispatch. I'm only interested in seeing dispatch stats. These are only the dispatch stats I got reported. So you can actually fine-tune exactly what you're looking for. Again, this is just a report on what you want collected, not how. So we haven't gotten to that interesting one where you're saying, I want to go past warm-up. Okay. Here's some other examples that would be also very interesting to try if you wanted to. You can also put the report flag, by the way, multiple times in the command line and distribute your report to multiple files if you want to do something like that. Okay, a definition file. This is the how. How do I want to collect a report? A definition file has the same concept of a content, but you can define multiple reports that you actually want to be able to do. And I'll get to these weird syntax things here in a minute. But in the report, for example, you can say what you provide your definition file. This is what you want collected for this report. And if you notice here, I have 2 reports. I have a report 1 that starts from time equals 0 and instruction equals 0, collect everything. The second report is essentially the same concept, collect the exact same thing, collect everything. I'm going to slightly rename the file. But this time I want to trigger it when a certain number of instructions have passed. Then start the report. So when you run this command, it'll generate essentially 2 report files. A Drystone 1 million instructions and a Drystone 1 million instructions delayed. Now, how did those get created? And go a little bit over here and disassemble this command line, just a hair. When you're creating reports, and the whole concept here, remember I was talking about you're doing a study, you're blasting this out to potentially LSF, and you're running hundreds of workloads. Each one of those report files, you don't want them colliding on top of each other with the same name. So you can actually specify and put wildcards, so to speak, within the report itself. Anything between 2% characters is a replaceable item by Sparta. So Sparta will replace it, but you have to specify what you want to replace. And there's a special command line option, report YAML replacements. As an example, report YAML replacement out base. If you find the word out base, replace it with Drystone 1 million inst. So that's what's happened up here. Out base up here will be replaced with 1 million inst. The format, of course, is over here on the right, text. And then the instruction start is 100,000. And yes, I didn't, that's not a typo. You can put the word K, M, anything like that. Sparta is smart enough to figure out what that means, so you don't have to write a whole bunch of zeros if you don't want to. It will replace all of those, essentially those items in here. If it doesn't find a replacement, it'll bitterly complain to you and let you know that you missed one. So I created those reports. Yep, I'm going to run it again, I guess. And when you do a diff between those two, you'll see that the actual number of instructions between those 2 different reports, one specifically is delayed and the other one is not, you'll see that the actual difference between them is 100,000 instructions, because that's what we said to actually delay the report on. So I wanted to go past 100,000 instructions, and I can see that I have total number of instructions is essentially, on the left-hand side is 1 million, on the right-hand side is 900,000. So I delayed the second report by 100,000. So I got through 100,000 iterations. We can look at this a little bit more detailed. We can actually do something more interesting, such as IPC, and you can see there's a slight IPC difference between the two. I guess I didn't type it right. Yeah, there's a slight IPC difference between the two. So now you see there is some effects of warm-up that are slightly in there. Dry stone's pretty small, and it fits and it caches, but we don't have it right now in this model in iCache. That's something we were working on as part of our charter of asking folks to help us with. The last type of report I want to get to is you can be very, very specific on the type of report you want generated. As an example here, this is another content where I'm simply saying, well, I know I'm running dry stone. Wouldn't it be cool if it actually, the report generated or calculated DMIPS for me based on how it ran? So you can actually do that. You can create a content file and you can be very specific of what you're looking for. I can rename, for example, core or RobStats IPC to all caps IPC. And then I can start doing some math. And this math was taken from the Drystone wiki page, essentially saying what is essentially the DMIPS operation of this specific machine based on the VAX VMS machine that they did their baseline off of. To do this one here is simply running that exact same report using the original report command, and then we can run it here. And as this one runs, I'm going to let it run for the full duration of the actual dry stone, which is about 2 million instructions. Now I've got a very succinct report, and that only tells me the DMIPS. So I can do clever things like that. You can do that for CoreMark. You could do that for, if you have SpecInt or any other type of workloads that you're looking at, you can do these type of things. Okay. So that's the whole concept behind report generation. That's what makes, in our opinion, the model the most useful. Time series. So one thing that's very interesting and something you want to be able to do is like, all right, I got a baseline number. At the end of simulation, it's output an IPC. Well, that's nice and all, but did it represent what really happened during simulation? If you ever done any kind of performance analysis, you may get something like where you run an application and its IPC comes out to 2 out of IPC 2. It comes out it's 2 and it's in a retire width of like 3. But you're like, oh, that's pretty good. But then you realize that if you look at an actual time series where the IPC is flowing through the machine, it may start out at 3 and then drop down to 1 and then come back up. And so the idea is that the average out is 2. And it's like, well, that doesn't really represent the workload. You want to know why did it drop? That's an interesting spot. And the only way you can find those is actually generating a time series. Using the same report mechanism and doing a time series definition file, you can do the exact same thing I did before, but in this time you actually say, I want to create a CSV file that represents those outputs. The trigger, instead of saying start a report and start generating that report, is instead what you use as a trigger. So you can say, when a specific counter in the simulator hits a certain value or is within a certain period of time, I want you to capture all the statistics and add a line to the CSV. Or capture what, what do you want me to capture? And for in this example, the core stats, everything. So this one would collect everything that's going on. This one here is the same kind of command. What I have here is a core time series definition file. When we run this one, it'll generate a very large, massive CSV file in the background. Column -t. -s, comma, and we called this file Drystone, 2 million instructions CSV. And so you can see that we have every single time 10,000 instructions, which is, or the period actually I said here was 100,000 instructions. Every single time 100,000 instructions finished, it caught and captured all the statistics one line at a time. So the instructions dispatched. So if you add up all these numbers, you will eventually you'll see that you would get to the total number of instructions that were actually executed. So it captures the difference between the last time it captured all the stats and the next time it captured all the stats. One thing I want to make very clear about how Sparta works and so forth, the counters and statistics and so forth that you define in the model for the report generation, where you do a report generation at the beginning, a delayed time series, which does this delta time series and so forth, never touches your counters, never touches your stats, and doesn't reset them. What it does is it just constantly grabs them and uses them and makes differences behind the scenes. So your counters from Sparta's point of view are completely read-only. That allows you to be able to make those changes. So you know that your counters will be accurate if you were doing something based on your counters internally. So lots of columns on this one. If you want to be able to view this, I did supply a small itty-bitty Python script that allows you to actually look at these things in a time series. And so this is a very mundane looking time series that is representing the data I just literally collected out of Olympia for dry stone for 2 million instructions. At the top here is the IPC, and you can see the IPC starts to improve most likely as we start hitting in the cache, right? So that's giving you an idea, but you can see it kind of wavers back and forth, but at the end of the day, you get a final IPC number. But you want to know why, for example, some of these items drop. And I only graphed a few of these statistics here. There are probably 40 or 50 other stats that you could throw into this Python script. It's very small, that it uses a matplotlib in the background to do this work. It's also included in Olympia if you wanted to play with it, or you want to build your own tools around it, or just essentially import the CSV into whatever you want to use those. So that is a time series report, and that's some of the power you can use out of this simulator to allow you to do detailed analysis. For example, when you see IPC drop, you can look across the board to see what other statistics and counters went up and went down with it, and it might give you a clue where to look where your performance bottleneck might be. Okay, so I have some other examples here you could try with a small core and the big core, and then you can plot the differences between the small and the big. You can see the difference in IPC, why you would have that, and I'll get to in a minute what the differences are between them. But when it comes to doing a detailed analysis, what you really want to do is get down to pipe out generation. So Arup mentioned this earlier. Essentially, pipe out generation is part of our Argos visualization suite, which is part of the MAP Sparta framework. What you can do and what you kind of get for free when you use a lot of the Sparta internal componentry like buffers and queues and pipelines and pipelines and pipes and so forth, you get for free pipe out collection. You can add more things to your pipe out collection if you want. The idea is these are, if you're familiar with VCDs and FSDBs, it's the same concept where you're essentially collecting data directly out of the simulator for pipeline visualization. This is the examples of how to actually generate those pipe outs. And I shorten them to only 100,000 instructions for each one of the microarchitectures that we have here, the big, small, and medium core. And then I went ahead and pre-built and visualized these already. And so I'm not expecting folks to be able to read this in detail, but one of the things to look at I have here on the left is the small core, which represents only one ALU, and on the right-hand side is a big core, which represents, I believe I have something like 3 or 4 ALUs. So you can see, for one, the pipeline going up and down is the pipeline. So at the very top here, we have decode, and then we have rename. I might be able to make it bigger. There we go. There we go. We have the top here, decode, rename, then we have a dispatch, and then we have the credit counts for each one of the units. And then we have the ALU block, the FPU block, which you have the ALU scheduler, FPU scheduler, and so forth, and the BR scheduler. Whether the data cache is busy or not, load store pipe, and essentially the reorder buffer, the ROB at the very bottom. And of course, it's kind of a pretty color, so it tells you and indicates where you are. Each one of these blank slots represents something's not happening. Going left to right is time. So this dark black line, you can think of time now. Everything to the left is time in the past. What has already gone through the core, and what's off to the right is time coming up in the future. And then you can increment this and thumb through it to see where the problems are. So for example, you can see the ROB is starting to climb and grow in size. So something is preventing ROB, but all of a sudden we have a really good drain over here. That's fantastic. We're getting good throughput. You know, those things you can look for. But at the same time, there's a bubble here. Why aren't we getting new instructions coming in the machine? These are things you can look at. You're looking at essentially the pipeline viewer. On the right-hand side is the big core. It's the same view, but if you can probably see there are more horizontal lines here which represent more units that have been actually added to this. And it's the same concept. You can page through this and see the differences in the actual machine, and you can start thumbing through things. This tool also has a little things such as find the next transaction, mark a transaction, look for things like that. There are a lot of tools like this already in the industry, a lot of tools out there that we would like to integrate with and so forth. But this is one tool that we right out of the box support. Okay, let's put it all together. So now we've been able to take the simulator, know how to run it, know how to get a trace, know how to actually generate reports, know how to look at other types of things. You can look and generate logs if you want to. I didn't mention that, but it's another way of doing it. Logs are another way where you can actually textually look to see where things are happening. It's a good debugging tool. But let's see if we can make Drystone run a little faster. This original command line here that I provided, it generates essentially that dmips output, which is what was here previously. And this one is running the small core. How do I know this? I set up Olympia, and I documented this in the wiki a little further up. I set up Olympia so that if I do not provide a microarchitecture to run, it automatically uses the small one. So the small one tells you it's got a dmips of about 2.3 per megahertz out of this configuration. So how do we figure out how to make this a little faster? What is the actual causing that low performance? We can start looking at the core report, but let's specifically look at dispatch. Dispatch is usually kind of a hot spot inside the core. If dispatch can't move stuff around, then something is obviously blocking it, and it's going to slow down the core itself. So if we just narrow down and rerun this with essentially the different report content and look specifically at dispatch stalls, we can figure out what's happening. Well, if we notice here that here are the dispatch stalls. So dispatch not stalled is a very good thing. We want most things not stalled where dispatch is actually making forward progress. If there are no ROB credits, that's obviously bad. The ROB's too small. LSU seems to be very busy, and we also notice that the ALU is extremely busy. Remember, in the small core, actually I didn't really say this out loud too much, but the small core only has one ALU. Drystone's a very integer-heavy benchmark. It'd be really handy if we gave it a second ALU. So one way we can do that is we can essentially increase the number of ALUs that are in the machine. You can use that using the YAML files and so forth. One way to do that is essentially create your own specific type of YAML file that you increase the number of ALUs to 2. So if I did this specific type of work right here, where I simply say, okay, I'm going to increase the number of ALUs, and just for now, we'll go ahead and ignore all the scoreboard information here. So now I have this thing called an ALU2 YAML. This ALU2 YAML increases and adds an additional ALU. Now, let's run that on Olympia. So if I give it a second ALU, will this improve Drystone? And I also want to generate the exact same traces I had before. Running 2 million instructions. Look at that. ALU busy went to 0. So obviously just adding one extra ALU actually helps Drystone in this situation. But that doesn't mean that you've solved the magic problems. It means just something moved somewhere else as far as the actual stalls and delays. Otherwise, Drystone would probably go up significantly. So the idea is that you're now being able to see, and if we can continue with essentially this experiment here, we can see that the dmips per megahertz would improve essentially with this configuration over the prior configuration. And that's a good thing. You're on your way to figuring out what is the way or the microarchitecture that I need to start building to actually make Drystone dmips improve. So that's the general concept of how this works. There are more examples here to continue with the tutorial. For anybody who would like to do it by hand, each one of these commands should work. Again, if we have any issues with it, please file an issue with us or make comments on it. But with that, I was going to go ahead and wrap up the tutorial. I wanted to provide an actual interactive view of how it works. These are commands that are available, should be working for everyone today. We'd love to have some feedback on this. But I wanted to make very clear that Olympia is still very much in its infancy here. It's a very simple simulator. Currently, the things that we don't support that we're looking for help in is operand dependency tracking. Briefly showed a little bit about the scoreboard stuff. We started the effort, but there's a little bit of work that has to be done to rename, for example, with actual physical register files and things like that. So if you're really into microarchitecture design, and want to help, this would be great. There's no branch prediction, although Arup and his team are working on a branch prediction API. So the idea is that Olympia can work within a branch prediction API to do queries as it reads from a trace. I got a branch, what do I do? Do I take it or not take it? And it will query an API. You can plug in your own branch predictors using this API. So if you're into branch prediction research, that's what this would be very helpful and handy to do, to see if you can improve your branch predictor. We don't have an iCache in this thing. We do have a Dcache and TLB, that is there. There is no execution pipelining, so each one of the ALUs, for example, blocks, finishes. In reality, real actual order cores will actually pipeline those, and we would want to add that support as well. These are all simple things that can be added over time. The idea was to get this in a couple of months up and running so we could provide it an introduction to this concept and get some immediate feedback and ideas moving this forward. We're looking, at getting academic help on this. We're also looking at just the community in general. So this load store unit's very simple. It's just a simple pipeline. A load goes in and it blocks everything until it's finished. And store goes in, blocks everything until it's finished. I mean, obviously that's very not good. And as you can see from Drystone and DMIPS, it's terrible. So if you improve the load store unit, and what's neat about Sparta is allowing you to do modularity, allows Olympia to do modularity. You can pull the load store unit out of Olympia and say this is terrible, and put in your own load store unit that you define. And you're up and running right away. Because what you do is you get fed from the outside, the instructions that are coming from dispatch. You can tell dispatch how many instructions you want it to feed to you, how many load store instructions you want it to feed to you, and then you just have to tell dispatch when to start and stop by doing typical normal control flow with using credits. So this is a very extensible model. The idea is to grow it, make it bigger than it is. Looking forward to everybody and people getting interested in asking questions about it and driving it forward. But hopefully this will give you a general idea of what you can do with it. Hopefully it gives you an idea of maybe the power of what you can make out of it. So that concludes it. Thank you. I think I have time for questions. Yes, sir.
Within this budget of transistors, what would be the best combination of parameters to use?
So your question is related to how would you actually use this model to build a cost model that represents actual hardware development, design, and cost on hardware. That sounds okay. So the idea is that if you added, as you were saying, is you add another ALU, how much would that add to my cost and hardware development and so forth? The idea is that you're asking a question of more or less of adding an ALU, does it even make a difference to what I'm doing for my customer workloads and applications and so forth? If it does, then you automatically know how much, because of the way you're doing your own hardware design, how much an ALU would cost. If you had people who were working on this, they know what needs to be done to add that ALU, the other types of routing you'd have to do for an out-of-order scalar processor, for example, read ports and write ports that need to be added. Those types of things, credits and information going back and forth to dispatch, all of that is part of your cost model.
Yeah, but I mean, if you put the cost model into the Olympia, then you can do 100,000 runs with different parameter combinations, and then use that to find a good solution.
You could. It'd be interesting to see if you could add something like a cost model like that to Olympia. That would be a very interesting piece of research. I've never actually tried that with any performance modeling I've done in the 20 years I've been doing this. Yeah, thank you for the question. Yes, sir. Yeah, I've actually received that question. What differentiates Olympia from Gem 5, for example, or Simple Scalar, or any other types of open source, a System C-based simulator, right? So those types of things. So the first thing I want to say is we're not in competition with any of these things. Yeah, I don't want to be that. The first thing, Sparta does work on, I'll address the System C even though you didn't ask that. The System C one, Sparta does work with System C based simulations and so forth, but one of the things that we've found with System C is if you are focused on doing Verilog, RTL synthesis and development and so forth, hardcore verification, that type of thing, System C is an excellent platform for doing that. But it is something for if you're a software engineering or software workload analysis and so forth, you want to work with a tooling that's more abstract and more forgiving to mistakes. Sparta-based models and so forth are more forgiving, and this goes actually into the Gem 5 statement. Gem 5 requires you to actually make sure it functionally works in order to get it through and so forth. That's the power of Gem 5. It allows you to have a full SoC design. But their development and their pipeline is very simple, right? And it needs to be. That's the way it's designed. It's a research tool. And so it's an event-driven or a single event that essentially executes and moves forward through the pipeline. Our framework is more or less keeping essentially, if you look at, there is no like main loop in Olympia. It's more like everybody is in that topology and everybody gets an opportunity to make forward progress. And because of that, it makes it very modular. So now I can pull out parts of Olympia, anything I want. I can create a different ALU and drop it in, and just recompile it and run it. While in Gem 5, you'd actually have to go and instrument all that code that's representative of that. And also, you have to make sure it functionally works. Otherwise, if Drystone doesn't run because you're trying an experiment of something weird and wacky, that's bad. And then you have to figure out what's functionally wrong. Trace-driven based right now, I'm not arguing trace-driven versus execution-driven. There are benefits to both. And one of the trace-driven one is I can do all kinds of really bad ideas. As you can see, as was mentioned here, we don't have operand dependency in this model. Gem 5 does. And we don't have operand dependency, but because of that, I can do all kinds of weird, crazy architectures, and Drystone still runs. So that's one of the benefits I like about it. It gets you started. You don't have to make sure it functionally works, and it's a little faster. Yeah. Any other questions? Yes, sir. Yeah. Yes, so the question was I showed essentially parameters and YAML-based and so forth. There's a way to actually provide a hierarchy of parameters. You can start off with a base set and then include. So for example, and I didn't really show this too well here, and I can show you here, in the architecture files, you have essentially a small, medium, and big core. If you have a medium core, the first thing that's in that line is include the small core. So you can actually define your basic set of parameters that you want your machine to always behave at, and define all of those in one large YAML file that is your base set, kind of like inheritance in C++. This is what the base behavior is supposed to be. Then you can create multiple configurations, multiple microarchitectures, defining that include, by using the include keyword, that specific base. Oh, okay. Oh, okay. Oh, okay, so you're talking about a top-level parameter that all multiple units can use that you want to be able to define on that. Yes, that goes into a little bit more discussion, a heavier, deeper discussion of how Sparta works, but those are actually handled with extensions. So extension parameters are the ones that actually define behavior across the entire simulator. You can think of it as like preferences for your user application. So for example, the execution topology, ALU 3. Who needs to know that there are 3 ALUs in the machine? Dispatch does. And the execution block needs to know. So it needs to know, I need to create 3 ALU issue queues. I need to create 3 ALU pipes. Dispatch says, how many ALUs are there? There are 3. Okay, I need to create 3 different ports to be able to send 3 different things. So you have multiple units in the machine, they're looking for these things. And I put them at the core 0 extension. So I think that answers your question, that you can define higher level parameters that represent behavior across the machine that multiple things can pull from. Okay, sure. Yes, sir. So what is the speed of Olympia right now? The speed of Olympia right now, depending on which machine you run on, right now this is an x86 Mac, but the M1 Mac, I understand, actually does much better. But Olympia right now, depending on, and this is an interesting question answer, depending on how well your microarchitecture performs, if it's like a really high IPC, Olympia can blast through it about 750,000 instructions as it is today. But if it's more complicated or it's delayed and so forth and takes more time to get through it, it can take, it slowed down, I think in this example here, it was probably running around 500K or less instructions per second. But this is a very rudimentary simple model. As it gets more complex, it will slow down. And we know that. And so the importance is to try to stay on top of that and try to make sure you do clever things with discrete event simulation. Yeah, if you're about 1 or 2 seconds for each instruction, million instructions that go by. We want to keep track of that. This one was built, this version of it was built with LVM, with LTO enabled and some other optimizations, which sometimes it can bring about price benefit, sometimes it's detrimental. We have to play with it. Yeah. As long as it's not under case. Yes, it's under case so far. Any other questions? Thank you, everybody. Appreciate it.